All right, so today we're going to be looking at an ellipse. An ellipse you can think of as a distorted circle, right? Imagine that you had like a bouncy ball and then you put some kind of weight on top of it. It's going to deform outwards, right? Which is kind of what you could imagine here. Imagine that we had this as a circle, we put some weight on top, and it just kind of deformed this way and became this ellipse. There's a much closer connection between circles and ellipses, which we will investigate during this conversation, but that's kind of the starting way that you can think about ellipses, is someone took a circle and just sort of smashed it in with respect to one dimension, and then it deformed the other way to sort of compensate. So just like with circles, there's a few different forms that our equations can take on, and we want to be able to deal with any of those, right? So while you can't see the whole equation here, this equation for this ellipse is a little complicated. We're going to have to do some work with that, just like we did with circles, in order to get it into a usable form that we can easily manipulate. Okay, so let's go over to our formulas here. So remember, we have the formula for a circle. This should look familiar to you. And we have our new formula for an ellipse. Well, notice for our circles, we have this r squared over on the right. Remember, if you take the square root of the constant, that gives you the radius of your circle. Well, with some of our other conic sections, we solve for 1 over here. In other words, you just divide by whatever number is on the right side of the equation. Well, let's just suppose for a minute we did that with the circle formula. Well, you're going to notice something all of a sudden, or I hope you notice, is that there is a huge similarity between the formula for a circle and the formula for an ellipse. In fact, at first, it's almost hard to tell the difference between them, right? So we take this top equation, you divide the left and right side of the equation by r squared, and you end up with this, which looks an awful lot like our ellipse formula. And we go, well, wait a minute, what is the difference? Well, the only difference is that in a circle, your denominators are equal to each other, and they're the square of the radius. But in an ellipse, your denominators are different from each other, but they still are the square of a value which is kind of like the radius. It's not the radius, but it kind of plays the same role, but for ellipses. And that might seem weird. Well, why is there two different ones? We're going to talk about that. It's because you have two different dimensions. So you need a length in each direction. But that's really the only difference. So it turns out like we teach circles and ellipses as if they're these totally different things with totally different formulas and totally different behavior. But the fact is, circles are ellipses. So the same way that a square is a rectangle, so any formula you have that you can apply to a rectangle, you can apply to a square. Well, we have the same thing here. Any formula you can apply to an ellipse, you can apply to a circle, which tells us something. We, in fact, don't really need the circle formula. Right? We teach you to learn these two formulas, and sure, it can be handy to have the circle formula, but the reality is you can just use the ellipse formula. You can use the ellipse formula for every ellipse. You can use the ellipse formula for every circle, because a circle is an ellipse. All you would do when you're dealing with a circle, these two denominators would be the same, and you can construct it the same way. Now, that's nice because then you have one way that does all your problems. All your circles, all your ellipses get solved with the ellipse formula. But there's nothing wrong with learning both formulas, circles and ellipses. And the reality is you're going to have teachers in the future who just expect you to know the circle formula, even though it's essentially the ellipse formula. So just be aware of that. I think a lot of students go on where they never make the connection between circles and ellipses. They think they're these two different objects. They're really not. They're really the same thing. Well, at least one way, right? Circles are ellipses. Not every ellipse is a circle, but circles are in the category of ellipses. So you can do all those with that formula. Okay, with that said, let's jump over to here. This is the ellipse that we're going to be dealing with, and we're going to take an analysis of this ellipse right here. The first thing that we want to do is put this in the completed square form the same way we did with circles. So basically, we're going to collect our x's and y terms together, and then we're going to go through and perform completing the square. It's really just like we did with circles, right? So we basically here, we've collected the x terms together, we've gotten the y terms together, and our constant is over on the right. So now you can see what we're doing here is I've factored the coefficient on my x squared, I have factored that out of just the x terms. We're not factoring it out of the entire equation. We're factoring it out of the x terms. So you can see the 9 got factored out right here. And then likewise, we took the coefficient on our y squared and we factored that out of the y term. So we factored the 25 out, but we've only factored the 25 out from the y terms. And then, of course, we still have 164 over here. So now we're set up for actually beginning completing the square. So what I'm going to do is I'm going to go in each of these parentheses and I'm going to figure out what I have to add. So let's play the completing the square game. So I've got a coefficient on my x, which is 4. So remember the rule, you take half the coefficient and you square it. So half of 4 is 2, 2 squared is 4. So I'm adding a 4. But we have to be careful here because everything in this parentheses is being multiplied by a 9. So if I put a plus 4 in here, that plus 4 is automatically being multiplied by a plus 9, meaning I've really added 36 to the left side of the equal sign. So that means that I have to add a 36 to the right side of the equal sign. Okay. Same as in here. When we do completing the square on the y's, half of 2 is 1. 1 squared is 1. So I write a plus 1 in here, and it really feels like I added 1 to the left side of the equation because I literally wrote plus 1. So it's very easy. This is a common mistake that students will then on the right side go, oh, plus 1 on the right. Because I wrote plus 1 on the left, so I should write plus 1 on the right. But remember, this plus 1 is being multiplied by a 25. So even though you wrote plus 1 on the left, you really added 25 to the left. So that means we have to compensate by adding 25 to the right side as well. So that's where those values came from. So then we're going to go through and just clean it up a little bit so we can, simplify things down. So we're going to factor what's in the parentheses and we're going to simplify our constant on the right. So by doing that, we get this. 9 times x minus 2 squared plus 25 times y plus 1 squared equals 225. That's the sort of the simplified version of what we have at this moment. Now remember in our formula, for the ellipse, since we're almost there, let's break this down. The h and k is your center of the ellipse the same way it was the center of your circle up here, right? We use it the same way. But notice over here on the right side of the ellipse formula, we divide by whatever number's there in order to get 1. So we're going to divide by whatever number is in our problem over there, which for us is 225. So see how we've got 225 over here, but we want that to be a 1. So we're going to go through and we're going to divide the entire equation by 225. Okay. And so when we do that, we get this step. So it's now 9 times x minus 2 squared over 225 plus 25 over y plus 1 squared over 225 equals 1. So that's all I did in that step was divide everything by 225. But notice there's some simplifying we can do. What about this 9 and this 225 here in the first fraction? What about this 25 and the 225 in the second fraction? We can definitely simplify those things down a little bit. So that's what we're going to do. That's our next step, is to further simplify as much as we can in this formula, so that we now get something that's a little easier to, the numbers are smaller, it's a little easier to deal with. So we have x minus 2 squared over 25 plus y plus 1 squared over 9 equals 1. We have it in the right form for our ellipse, so we can see what the center is just by looking at our problem. And then what about these a squared and these b squared values? Remember I talked about how it's kind of like your radius up here. Remember this r squared value? When you take the square root of that, you get the radius, and that really, if you put it in the same form, it ends up in the denominators. The only difference is here we get two different values for these. They're not a radius, but you'll see when I work on the graph, there's a relationship between the radius and these values. But what you want to remember is we're going to take the square root of this value, a squared, but we want to remember that's in our x dimension, so that's horizontal. And we're going to take the square root of this b value, and that's under our y. Y's are vertical. So when we take the square root of a, that's going to tell us something horizontal about our graph. And when we take the square root of b, that's going to tell us something vertically. Basically, the horizontal and vertical parts of this equation are being distorted differently by these different values in the denominator. And that's why you don't get a perfect circle. You get this distortion of an ellipse. Right? But again, if the two values are the same, that's still an ellipse. It's just a regular ellipse. It's like square square to rectangle as circle to ellipse, right? Okay, so by going up here, we can see what? We can see that our center is at 2, -1. We can see that this value we're going to grab here in our horizontal dimension, that's the square root of 25, which is 5. Over here, we're going to grab the square root of 9 for our vertical direction, and that's 3. The square root of 9 is 3. So we want to remember those. Our center is at 2, -1. We're going to want the number 5, and we're going to want the number 3. So let's jump over to our picture now. So, I've kind of cheated in that, I've already got this thing graphed, but you're going to see how to do this in just a second. So there's our center, 2, -1. So our formula is checking out. But now we have this 5 from the square root of 25 and this 3 from the square root of 9. Where do those come in? Well, if we take a look at our center, and imagine we haven't drawn this circle yet, but I'm doing this for illustrative purposes. If I start here, remember 5 corresponded to the horizontal direction, and I said it's kind of like a radius, but it's sort of it's the analog for ellipses. Well, let's start at our center and let me count horizontally 5 units. So I go 1, 2, 3, 4, 5. Sure enough, that puts me right on my ellipse. And if I start here and I go 5 units to the left, 1, 2, 3, 4, 5, that puts me right on the ellipse. Now, what about the 3? That was under our y, so that's giving us about a vertical distortion. So if I start here at the center and I go up 3, 1, 2, 3, oh, I'm right on the ellipse. I go down 3, 1, 2, 3, that's right on the ellipse. So in other words, just like when you have your center and you calculate the radius, you can just count over, up, and down and plot some points and draw your circle. You can do the same thing with an ellipse. You plot your center, and then you grab the square root of 25 under our x, and you go left 5 units, right 5 units. Then you grab the square root of 9, which is 3, under our vertical distortion, and you go up 3, down 3. Then you have 4 points, and you can kind of roughly fill in your ellipse. The reality is, in this day and age, you're never going to draw an important ellipse by hand, right? Because if you're doing some kind of presentation or a project or something that's important, you're not going to be sitting here trying to draw like ellipses are hard to draw. They always kind of end up looking like a potato or an egg or something like that. So it's really nice to have a computer do it, but you need to understand the mathematics behind what the computer is doing to graph the ellipse. Otherwise, you're never going to be able to design anything with ellipses or circles or use them in any kind of meaningful way. So we can kind of see that. Let me show you here when we've got, so there's where I'm using the 3 that we got from the 9 from the y value. So you can see we go up 3 units, down 3 units, and that gets us to the ellipse. And then I'm going to go left 5 units, right 5 units, and that kind of gives us the basic shape for filling in our ellipse. Okay, those, by the way, these are called the major and minor axes, whereas a radius has that sort of constant distance all the way around for a circle. An ellipse has one in a vertical direction and one in the horizontal direction, and they're different, but they're easy to tell because you just look what variable it's under and go, oh yeah, x's are horizontal, y's are vertical. That's basically always true. So then we get our ellipse, and then, you would fill it in. We don't actually have the circle, and then, or the center, and then right here, there's your ellipse that you're left with. We've properly graphed that thing. So we started with it in an inconvenient form. We did some algebra and completing the square to get it in the convenient formula that we're used to, and then we use that information to come over and graph the thing. Okay? So that's ellipses.